Hi, folks. Today we're going to talk about the history of mathematics. This is a very, very big topic. Before we begin, history is a very tricky thing. Humans have existed for roughly 200,000 years, and culture shifts and change are constantly happening. They are created and destroyed. We have seen cultures exist. And when we look at how they have migrated throughout the last 200,000 years, we can see that they started by going north and then something happened and they died out and then they basically restarted everything. This pattern kind of describes how math has grown. When we look at the migration patterns of earliest humans, we can see that they started by going east before some of them moved more northernly, more went further east, some went very far east. Uh, Depending on when civilizations settled, it really determines how much math they created. That said, it's impossible to cover everything in one PowerPoint. This would be an entire course devoted to the history of mathematics. We are going to kind of cover as much as we can get away with and give you the broad strokes for history. Yeah, there's a lot of math history. And so, how do we begin to examine math history? When we look at the big picture of math education, it's important to think about it as a tree with branches. As cultures are created and grow, we develop new maths. New branches are added to our tree. Some branches have been lost to time. Some can barely be seen because they're covered by other branches. But all the branches add to the tree. And so our goal is to understand how all of these branches connect together to better understand the tree itself, the tree of math. And so, before we start, why do cultures make mathematics? Well, with 200,000 years of math to cover, there's a few major themes which we are going to see. As cultures grow or face new challenges, their need and desire for different math tools has grown. Generally, we can think of the reasons as being philosophical or practical. And it really depends on where different societies are at. If they are worried about barbarians coming and attacking them, then they may be less likely to focus on the philosophical sides of things, and they'll be more interested in the practical side of things. If most of their needs are taken care of, then they can focus more on the philosophical side of things. And so, some of the practical reasons that people develop math or cultures have developed math: agriculture, commerce, engineering, navigation, society. How do we keep track of people? How do taxes work? And war. War is a very big one. Philosophical reasons. Some do science for science's sake, and you need a little bit of math for that. Religion has been a major motivator. There's also art and architecture and recreational math, which is math for math's sake. Here is a fun little outline I found from a book by Howard Eaves in 1953, which kind of showed the broad strokes. And I really liked the way this explained little bits and pieces of where things were and how they all fit together time-wise. Uh, I started with this and then expanded it to focus on a few other things because this does not cover everything by any stretch of the imagination. And certainly there have been advancements since 1953 as well. But this gives us a starting point. And so, talking starting points and starting points and starting points, let's actually start. Proto-humans and non-humans. And so mathematical discovery predates humans, as even animals can display basic mathematics. And so when we're talking about basic mathematics, we're talking about things like distance and measure and navigation and space, some level of physicality. Construction of a nest, that is a mathematical object. Understanding more versus less. And then ants, for example, are able to create very advanced structures. While some patterns are natural amongst animals, other mathematical structures are well understood by animals and used to improve their survival. We then have prehistory humans. And so this would be everything from 200,000 BC to roughly 3,100 BC. Much of the mathematics of old is lost to time. We don't have any record of it. We do have some records of things, though. For instance, knots. Knots date back to roughly 100,000 years ago. There's evidence of tally marks and basic counting principles going way back. The quipu of the ancient Inca date back to the dawn of history, around 3,100 BC. Dice similarly date back to around 3,100 BC. During this period, it's assumed mathematics was primarily used for practical purposes like agriculture, pottery, weaving, and whatnot, but we really don't know. There isn't much record of it. And one of the big reasons is the types of material that things were written on. They just weren't meant to last quite that long. One of the earliest and sometimes considered the oldest mathematical tool we have is this one. It's called the Ishango bone. So the Ishango bone was discovered in the Congo, and it's a bone with numerically interesting tally marks on the sides, and a piece of quartz embedded in the top. We think that this might have been used for some form of counting or tallying or something like that, but really it's tricky to determine. Like I mentioned down here, it is dangerous to apply our modern sensibilities to a tool this old. We do not know what the people of Ishango, Africa were doing in 20,000 BC. We just do not have record of it. But there are signs pointing towards this being some type of mathematical tool. When we leave prehistory, and so roughly 3,100 BC, we start to see that the mathematics that we can observe is really dependent on the types of materials that folks were using. And so at a certain point in each culture, they migrate from oral traditions to written traditions. And of course, colonization meant that some civilizations never really got that opportunity, which is truly tragic. Different cultures made this transition at different times. And so in Mesopotamian Egypt, it was around 3,100 BC. Around 3,100 BC, people started to write stuff down. The important stuff that they wanted to write down, they wrote it down. In China, this was around 1250 BC, and in Mesoamerica, it was around 1 AD. And so we then can determine what people were doing mathematically based on what was written, provided those writings lasted. And that's really some of the challenging bits. Early Chinese works were written on tree bark or bamboo. Tree bark deteriorates very quickly, and bamboo is flammable. And so that caused very big challenges when it came to understanding what ancient Chinese were thinking about mathematically. Egyptian papyrus, similarly, does not do well when it comes to time. We do still have some of the ancient papyruses, but most of them are long gone. Bone and clay, though, those last. And so when we think about bone, that was used in Africa, and Mesopotamia used clay. And so those are much better suited to last through time. And that's where we start to see tablets. Clay tablets, we can actually still view them and see what people were thinking about back then. In North and South America, again, this is where we get into some trouble. As one of the last places humans migrated to, roughly 15,000 to 8,000 years ago, settlers in the Americas were at a disadvantage in developing mathematics. Colonization cut many of these efforts short. Much of the mathematics used was practical math related to agriculture, weaving, and construction. That said, there are many interesting achievements by the Inca, Mayans, and Aztecs. And so, for instance, quipus. Quipus are knotted tools for keeping track of information. In particular, how do we keep track of how many people are in a certain region? Well, they used quipus for that. North American tribes used notched counting sticks. Mayan numerals utilized a base 20 system and a similar structure to the Babylonian numerals, which is kind of fun. And then the Incan constructions and engineering demonstrated advanced understandings of geometry. let's turn it towards Egypt and see if we can follow that path for a while. And so Egyptian history is ancient even for the ancients. To the right, the Narmer Mace Head, 3100 BC, displays information about a great war, displaying in numbers the animals and humans, 120,000 which were conquered. The pyramids of Giza were built in 2600 BC. And to understand just how long ago that was, Cleopatra wasn't born until 30 BC, meaning Cleopatra is closer to the modern age than she was to the pyramids of Giza. Their engineering skills demonstrate a strong understanding of mathematics, and they had written numbers as far back as 3100 BC. That's substantial. Much of the information about the ancient Egypt was written on papyrus, which is brittle, deteriorates, and has been lost to time, but not all of it. So a handful of papyrus demonstrates how computations were used for daily life, such as the Rollins papyrus, which was 1350 BC, which details bread consumption. Much like Roman numerals, they did not use a positional number system to represent numbers. The number system can be seen to the right. And it was used into the first millennium AD, but it was tricky. Every time you needed larger numbers, you needed to create new symbols. And that makes it kind of tricky. We also have the Rhind papyrus, which gives a deeper understanding of what type of math they were exploring. And so, yeah, the Rhind papyrus, 1650 BC, is a detailed document of ancient Egyptian mathematics. It demonstrates basic understanding of arithmetic, fractions, geometry, including areas and volumes, algebraic ideas, and number theory patterns and problems. This basically informs us that they had some strong math notions going on at the time. And often, though, they're overshadowed by Babylon and Mesopotamia. And so Mesopotamia, ancient Babylon, was a culture in modern-day Iraq, which thrived from 3100 BC until the fall of Babylon in 539 BC. Much of our understanding of their ancient math comes from clay tablets, which date back to 1900 BC to 1600 BC. To the right, this one is Plimpton 322, which demonstrates their number system and is a listing of Pythagorean triples. And so again, we have evidence of geometric understandings, of algebraic understandings as far as what do these numbers represent. And their number system, it was a positional number system. And so it made it so that they could do larger quantities of things. Babylonian mathematics is often viewed as highly advanced, particularly compared to the Egyptian math. This is often attributed to Babylonian being more central on the trade routes. And so if you're on the trade routes, you want your numbers to actually count. It's a math joke. It is known that the math predates written history, but we do not know by how many millennia. And so they were doing math for a long time before we have record of it. They used a base 60 system, which we still use today for things like clocks and degrees. And it made things like early fractions possible. To the right are the Babylonian numbers. And you can see it's a base 60 system. And so once you hit 60, well, then we add a new value to the left, but then it's the same symbols that we were using before. And so that makes it so that the structure doesn't require additional values to be added, or additional symbols to be added every time we are getting to larger numbers. What we know about them, they understood the fundamentals of arithmetic, algebra, and geometry. They had pi approximated as 25 over 8, and the square root of 2 they had approximated to 6 digits. They understood the Pythagorean theorem very clearly. They could approximate solutions to the quadratic and cubic equations, and they even developed a few calculus techniques, such as the trapezoid rule. Many later cultures used Babylonian mathematics as a starting point. Essentially, as cultures would get destroyed and they would have to start rebuilding everything, they'd always say, well, what did the Babylonians know? And that was their starting point. Which kind of leads us to the ancient Greek mathematics. And so ancient Greek mathematics, I put some timestamps from 600 BC to 450 AD. It spanned about a millennium, but to understand it, you really have to think about the history. Greek mathematics is more about language utilized. This is not the mathematics of Greece. This is mathematics which was done in the Greek language. Thales from 600 BC came from modern Turkey, and much of the Greek accomplishments occurred in Alexandria, which was here in northern Africa. Alexander the Great conquered a large portion of the world during this period. And you can see here, this is where Alexander's empire was at its largest, and it was huge. The mathematics that we attribute to Greeks is really the mathematics which is surrounding the Mediterranean Sea in this time. And so a lot of it focused on Athens, but a lot of it was focused in Alexandria. And there was really a shift that happened about midway through. We'll get there once we talk about Euclid. To start with, though, let's talk about Pythagoras. Guy was crazy. There's more myth and legend around Pythagoras than there is actual knowledge. And it makes sense. This was a very, very long time ago. What we know is he learned his mathematics in Egypt and Babylon. He had a semi-religious society called the Pythagorean Brotherhood in southern Italy. And there they studied mathematics, philosophy, developed a rigorous approach to music, and had a focus on body, mind, and soul. They were a bunch of beatniks hanging out in the backwoods. Most mathematical ideas historically attributed to him predate him by Egypt and Babylon. And so, for instance, the Pythagorean theorem was not invented by Pythagoras. It was just something that they studied a lot. One which is likely correctly attributed to him is the idea of the incommensurable ratios or irrational numbers. The idea that some numbers may not be able to be represented by a fraction of whole numbers. This is like the square root of 2. The square root of 2 is an irrational number. And there in ancient Greece, they focused on this idea of the proof as being something important. And when we get to this square root of 2 being an irrational number, well, that doesn't really help with a lot of practical things, but it is an interesting math fact. And we can start to see how we can later use some of these ancient math facts to build larger mathematical structures. But this right here, this was one of the first cases where we're doing math for the sake of math. And we see this a lot in ancient Greece, in particular in Athens. And so for many hundreds of years, philosophy and great thinkers developed many of the modern structures we have today. So from Thales and Pythagoras came Zeno and Democritus, then Socrates and Hippocrates, then Plato and Diogenes. Oh, I like Diogenes. And eventually Aristotle. Ideas of how governments should run, the purpose and goals of education. These were big thoughts. They were in times of peace, and with that, they were allowed to think. Mathematics as a form of philosophy flourished during this time, and it was part of the classical curriculum developed by Plato, which was used throughout the Middle Ages. The idea of the trivium and the quadrivium. So trivium was grammar, logic, and rhetoric, and the quadrivium was arithmetic, geometry, astronomy, and music. And given how closely music was tied to mathematics at the time, the quadrivium had a lot of mathematics in it. All of this was about structure and the structure of structures. And that's where mathematics really strives. To the right, I have an image of Achilles and the tortoise, which is one of Zeno's paradoxes. One of the challenges at the time is they didn't have calculus yet. And so they struggled with understanding certain ideas. And Zeno's paradox illustrated one, the idea that it's impossible for the great runner Achilles to actually catch up to the tortoise, because after a certain time, Achilles will have made it closer to the tortoise, but not past him. And then at a later time, he will have still gotten closer, but not past him. And this will continue forever. Euclid was where things started to change, and we still are big on Euclid. Euclid formalized geometry. His primary work is the Elements, which introduced what we now call Euclidean geometry. Many of the math topics in the Elements already existed, but it formalized the idea of plane and solid geometry, expanded on it, and formalized a number of proofs. The geometry is still taught in many places using this book. This book has been around for 2,300 years. It's still used to teach math. Following Euclid, the center of mathematics remained in Alexandria. And so this is where there was a shift from Athens being one of the major hubs to Alexandria being one of the major hubs. And so in North Africa, with mathematicians like Eratosthenes and the Library of Alexandria being in Alexandria. One of the things that Euclid did was he developed an approach to mathematics which was new. It's called the axiomatic approach to mathematics. The idea being, if we take a set of things which we recognize to be most likely true, or some structures which we can actually see and have some understanding of, well, if we take those ideas to be true and call them axioms, then we can ask the questions of what other things must be true in light of those starting axioms. And then we can also ask, what happens if one of those axioms isn't true? This has been a strategy for approaching math for the last couple thousand years. And we still do that today. We observe things and then we say, well, what if that's not the case? And what if that is the case? And what are we able to prove based on all of those different situations? End of Greek mathematics. Yeah, all good things come to an end. And so the conquests of Alexander the Great were eventually overtaken by the Roman Empire. The Roman Empire adopted many aspects of Greek society. As the Roman Empire slowly collapsed, philosophy and mathematics became less prioritized. The Library of Alexandria became underfunded, eventually vandalized and destroyed, and Attila the Hun and other tribes invaded, leaving Europe into the Dark Ages. Yeah, and so by around 400 AD, there was no ancient Greece anymore. Everything in Europe had kind of fallen to the side as everyone was focused more on survival. And so let's transition to ancient China. And so ancient Chinese history, 8,000 BC to 1,000 BC. And so we know humans migrated to the east, in particular in China, around 50,000 years ago. Artifacts show earliest regional cultural development around 8,000 BC along the Yellow River. By 4,000 BC, there were a number of villages of various size, and one of the larger ones was Yangshao village in Banpo, which had 600 people. Pottery, language, mythologies began to develop. This was very, very similar to what was happening in Babylon, the Tigris and the Euphrates River. All of the stuff that was happening there was also happening in China. Up until roughly 2000 BC, these smaller villages developed relatively independently. Some grew more wealthy, others grew more aggressive, and this period is sometimes referred to as the period of 10,000 states, and it was viewed as a time of warfare. As one tribe would get more wealthy, someone might try and take them over, and, well, there wouldn't be more wealth there. Following a great flood, similar to what happened in the West, some of these villages started to unify, and the first dynasties began creating larger city-states. And so by around 10,046 BC through 256 BC, during the Zhou dynasty, culture made great advancements in agriculture, technology, art, literature, and the sciences. If it helps, think of the Zhou dynasty as comparable to the ancient Greeks. They were doing the same type of mathematics and studies. To the right is the sundial of astronomy and calculations, which is attributed to early Zhao. The Chinese sage Kongji, known as Confucius, was an influential philosopher and scholar of Zhao. The last years of the Zhao dynasty saw a greater push for education and philosophy. Again, when there is times of peace and people are able to sit and think a bit, there are great advancements in mathematics, philosophy, education. A lot of good stuff happens. Until a lot of bad stuff happens. And so this is the burning of the books and burying of the scholars in 213 BC. An image of it is given on the right. And so the Qin dynasty unified China under a single ruler. The Qin armies overtook the other states until all of China was under their rule. Under unification, there was a great purge of scholars and philosophers, and the new emperor sought to focus instead on the future. Fact and fiction are very blurry about this at best. And so we do have some ideas of what occurred. We do have some stuff from before the Qin dynasty, but much of it is just lost. And we do not know specifically what people knew, what people didn't know. There was a purging of information. And as soon as that happens, it's all just kind of gone. And it's tragic. From a math perspective, the emphasis changed from a philosophical view of math to a more practical approach to math, which remained until the modern era. And so let's turn to ancient India. India began to develop formalized mathematics around 1200 BC, and it developed through a series of philosophers and scholars. Unfortunately, it was an oral tradition until about 500 BC. So again, we have this transition from oral traditions to written traditions. So in the early days, they had a fair understanding of fractions, Pythagorean triples, and whatnot. Pingala understood summations and combinatorics. Jainism developed a more formal approach to mathematics. To the right is the Bakshali manuscript from roughly 300 AC, which gives us insight into Indian mathematics. One of the big things that came out of it, though, was the number system. And so while Europe entered into the Dark Ages, India mathematics flourished. And so from 400 AD until 1100 AD, there were a lot of very large advancements in India. And so the development of zero, negative numbers, fractions, square roots, quadratic equations, the development of the Hindu-Arabic numeral system, which we use today. It is suspected that the base 10 system may have been inspired by Chinese counting boards, but as you can see, we had this idea of 10 numerals, some of which still look kind of similar, and it's turned into what we currently use today. Symbols were formalized in different ways across the centuries, but this is where our numbers come from. There were also great advancements in algebra and trigonometry. And that's where we start seeing the Arabic Persian mathematics come to the forefront. And so by 750 AD, the Islamic Empire stretched from India through Africa and into Spain. As they expanded through the region, they translated all of the old Greek text, and a new generation of mathematics philosophers were born. They developed new techniques in geometry, combinatorics, and most notably, formalized algebra. One of the largest accomplishments was this formalization of algebra. So Muhammad ibn Musa al-Khwarizm created a formal written approach to algebra. Similar to Euclid, Al-Khwarizm took existing mathematics from Indian, Hebrew, Greek, and Babylonian math and extended it. He formalized approaches to solving linear, quadratic equations, the idea of balancing the sides of an equation and using substitutions. These were very large advancements, which are things which we use today. The one big difference between what they were doing and what we were doing is symbols. They didn't really use symbols. And so if you look here on the right, this is an algebraic expression, and it's actually written in words as opposed to using mathematical symbols. That's one big difference. That came later. And so now let's go back to medieval Europe and see what was going on. And so during the early medieval period, the Dark Ages, Europe became very religious. Boethius ensured that monasteries translated works of arithmetic and geometry into Latin. The idea being, hey, Greek might not last, and so let's get it into a more common language. Of course, Latin was a dead language, but they translated in there so that future generations would have it. Gerbert Aurillac, oh, I'm going to mispronounce that one, traveled to Spain, which at the time was part of the Arabic Empire, to learn mathematics. He learned about the abacus and Hindu numerals, and science lost to Europe with the Greeks. What he did then was he reintroduced these concepts to Europeans and integrated it into cathedral schools, and then became Pope. And so there became a greater push for having mathematics as part of the curriculum again. And this is around 1000 AD. And so starting to come out of the Dark Ages, but we're still in the medieval Europe, and so there's still lots of issues going on. But we start to see that everything's coming through Spain, and we're going to see that continue. And so Leonardo da Pisa, also known as Fibonacci, was the son of an Italian merchant who was brought up in Bougie, which is in modern Algeria. With an interest in mathematics, he learned the subject on his trips through Egypt, Sicily, Syria, and Greece. He learned a substantial amount of theoretical and highly applicable mathematics from throughout the region. He then wrote a book, Liber Abaci, which became very popular. It introduced the Hindu-Arabic numeral system for the first time, including zero. It taught how to use an abacus to do accounting and banking, and it introduced things like the Fibonacci sequence, which actually originated in India in the 600s, and other number theory problems. Europe changed because of this book. Europe changed because of Fibonacci. He gave them a new tool set for doing computations. And it was stuff that he learned while traveling the world with his father. And so definitely very powerful. And this started to see a change in what folks were interested in. And so beginning in the 1200s, modern universities began to pop up in Italy, the United Kingdom, France, and Spain. Mathematicians Tartaglia, Cardano, Ferrari, and others advanced algebra to create clearer solutions to the cubic equations and developed complex numbers. Mathematical astronomy became popular, and new tools were developed to understand the stars, and basic trigonometry became popularized for navigating the seas. With the popularity of universities in Europe, it became the center of math education through the early 1900s. And here we can see Oxford in 1810 and 2015. Not much has changed. It's been around for a very long time. And so now, around the 17th century, and so in the 1600s, we start to see some things change again. And so much of the mathematics of the 17th century focused on astronomy, navigation, trade, engineering, and war. It was understood that math was a tool to do these things better. And so we had to learn how to do it better. Napier and others developed logarithms, which were needed for measuring larger quantities. Algebra remained quite popular. It was still more or less done in words, though, so that was kind of problematic. Modern symbols started to appear for multiplication and division. Galileo, Kepler played around with planetary motions. Pascal developed and reintroduced many geometric and number theoretic problems and counting principles. But the most important thing that happened was René Descartes. I like Descartes. So Descartes, for me, is what really changed the old math into the new math. Before him, there was the algebra that existed where everything was written out in words. He developed the modern symbolic notation for mathematics. He also developed algebraic geometry, the idea that geometric problems can be solved algebraically. as well as analytic geometry, which is our modern approach to graphing. When you think about graphing, modern algebra wouldn't be a lot without the idea of a graph. Most of the modern fields in mathematics wouldn't be much without this idea of a way of measuring things. And Descartes came up with this approach. Fermat had similar thoughts regarding conic sections, but Descartes' Cartesian coordinate system, the rectangular coordinate system we use, is really a very large shift. And after that, calculus came around. And so with the development of the Cartesian coordinates, formalized calculus was developed by many mathematicians. For simplicity, calculus is the study of limits, rates of change, and areas under graphs. Fermat developed the difference quotient definition of derivatives. Wallis and Burrow introduced basic integration formulas, which is the area under curves. But Newton and Leibniz really made calculus what it is. They each discovered and formalized calculus independent of one another, and their approaches are slightly different, each with its own value. When you think about what we typically teach today, we focus more on the Leibniz approach, but the Newton stuff does pop up when you're talking about physics. Additional calculus tools developed throughout the 1700s as well. And so Lagrange developed a new notation in 18th century. The Bernoullis, De Moivre, Taylor, Maclaurin, Lambert, and Laplace all made very large advancements. And even into the 19th century, Riemann, Fourier, and Cauchy all made very big changes to how we approach calculus. And we still use all of that stuff. The next big change was Leonhard Euler. Euler did a lot. While many of the 18th century folks were focused on improving calculus, Euler did a lot of other stuff. So he was born in Switzerland, but spent most of his life in Russia and Berlin. He developed and formalized modern pre-calculus. He went back and explored Fermat's number theory and developed the fundamental theorem of algebra, the idea that things can be factored. And then he developed a whole bunch of math. He popularized the symbols for pi and e. He developed topology and graph theory. He developed power series and solved the Basel problem. He connected exponential and trigonometric functions through complex numbers. That was a very, very large thing right there. And then he touched on physics, astronomy, engineering, music. He did a lot of stuff. Yeah, he published many papers, and he developed just large swaths of math. Oftentimes, when we're discussing what we should name something after, we always defer to the second person that discovered it because the first person was always Euler. Euler did a lot of math. But this brings us into the 19th century, where things started to change a little bit again. And so the central theme of the 19th century was formality and proof. And new branches of math started to flourish. And so we're starting to come up with ways of understanding what math is. We're trying to answer the question, what is math even? And so Gauss was a big one. He was a child prodigy who contributed to algebra, analysis, probability, differential geometry, just a little bit of everything. Much like Euler, he had his hands in a lot of different math. Others were a little bit more focused, and so Abel, Galois, Hamilton, De Morgan, and Noether all developed new branches of math related to abstract algebra, which was all about understanding the properties of algebra and how we can apply them to other things. We also started to see modern logic be developed as far as what do we mean by truth? What do we mean by something not being true? How can we develop a structure to logic itself? Set theory and topology became clearer as fields of study. We then have Jacobi and Dirichlet advancing differential equations and dynamics, which were first developed by Newton. We then have matrix algebra, which is like linear algebra, which was explored in greater depth by Cayley, Sylvester, and Hermite. Projective geometry and analysis. Analysis is a very large branch of mathematics. It's like the formal approach to calculus. Were developed to better understand n-dimensional geometry and non-Euclidean structures. And then discrete math and number theory were also being reimagined by Cantor, Poisson, and others. I mean, in the 1800s, this is when we really start to see people model their approach to mathematics after Euler and try and explore broadly and deeply what different topics in mathematics might be. In the early 20th century, in particular 1900 AD, a fellow named David Hilbert, who was one of the most prominent mathematicians of the time, basically said, we need to stop, take a break, reconfigure, and then he gave everyone a task. And so he gave a talk at the International Congress of Mathematicians, and there were a lot of mathematicians who came just to see it. He listed out 23 problems which he viewed as the most important and influential to the field of mathematics. And mathematicians from all over set out to solve these problems. And in doing so, they created new mathematics. That was really what defined the early 20th century, is this direction which Hilbert gave to everybody. Well, a lot of stuff happened in the 20th century. There was the Great War, and then there was World War II. And those had major impacts on what we did mathematically. And so World War I and World War II emphasized on the importance of mathematics and national security. We then had the space race, which ensured a little bit of funding for it. We then had differential geometry, which became a major topic following Einstein and Hawking's contributions to physics. We then had computers, technology, that allowed us to do things which we had never been able to do. Some fields have become more abstract, allowing for greater tools to be developed. Abstract algebra, at this point, it is almost unrecognizable from its algebra origins. A lot of that work was done in the 1800s, but it's continued on. And then formalists tried to develop universal mathematics. And so is there one thing which is mathematics and describes all of mathematics? And Gödel proved that it was impossible to prove some things. That really changed the idea of, is there one way to prove everything? Well, nope, some things can't even be proven, and we can prove that they can't be proven. There was then the Bourbaki group, which was a group of mostly French mathematicians who developed definitive texts for a variety of math fields. Basically, they said, we want education to be free to everybody, and so we are going to create a set of textbooks which will summarize these large fields of mathematics which had been developed the last few hundred years. And that brings us to the present day. And so, as mentioned, this has just been a brief introduction to the history of mathematics. There are many cultures not included here, and they are definitely worth investigating. You should ask questions about history and seek out the answers, and this shared history brings us all together. Oh, isn't that sweet? Really, when we think about the history of mathematics, it's the history of people, and that's the bottom line. We can go very, very far back, and we can look very recently as well. And we can kind of chart a path for how things went from those early days of just counting to where we're at today, where we have a couple dozen major branches of mathematics, which have been explored quite deeply. That said, I'll let you get to work exploring where you find mathematics in the real world, with a focus on how things have moved and changed over the last few thousand years. Good luck, folks.